So in this problem, we've got a car C that's moving forward with some velocity and acceleration that's known. There's also a drone D that's following a curved path that also has a currently known velocity and acceleration at this instant. We're asked to find the velocity and acceleration of the car as observed by the camera on drone D. So if we were sitting on drone D, how would it look like the car was moving? We're going to do this using rotating frames analysis. We'll apply our rotating frame to the drone D. So it has to go on the object that's rotating, and that's drone D, following its curved path. Part A, we can write our rotating frame velocity equation. The velocity of the car equals the velocity of the drone plus the angular velocity of the rotating frame, or drone D, times the distance between the car and the drone, plus the velocity of the car with respect to D in the rotating frame. This is what we're asked to find. We know the velocity of C, we know the velocity of D. The angular velocity of D is going to be the magnitude of the velocity divided by D1, and we can see from the direction it's in positive K. The distance, RC with respect to D, is going to be the distance D2 in the negative I hat. When we write this out, we can say that BC in the J hat direction equals the magnitude VD, also in the J hat direction, plus VD times D2 over D1 in the negative J hat direction. So K cross negative I is negative K, plus the velocity of C with respect to D in the rotating frame. We reorganize this, and the velocity C with respect to D in the rotating frame equals the velocity of C in the J minus the velocity of D in the J plus D2 over D1, the velocity of D in J. Sub some numbers in, that's 12 meters per second in the J minus 9 meters per second in J hat plus 3 meters divided by 7.5 meters times 9 meters per second, also in the J hat. And we end up with 6.6 meters per second J hat. So if we were viewing the film from the drone, we would see the car moving again in the J direction at 6.6 meters per second, which is actually much less than the car's actual velocity. We want to go on to examine the acceleration of the car as seen by the drone. We can write our acceleration equation. We're told the acceleration of the car equals the acceleration of the drone plus big omega dot cross RCD minus big omega squared RC with respect to D plus 2 big omega cross VC with respect to D in the rotating frame plus AC with respect to D in the rotating frame. And again, this relative acceleration is what we've been asked to find. We're told that the drone is traveling with a constant speed. That means the acceleration of the drone equals 0 at this instant. It also means that large omega dot also equals 0 because it equals the magnitude of acceleration of d divided by d1, and that's equals 0. So we can rearrange, and we find the acceleration of c with respect to d in the rotating frame equals the acceleration of c in the j hat plus omega squared d2 in the I hat minus 2 omega times vc with respect to d in the rotating frame, also in the I hat. And then we can sub some numbers in for that. We've got 2 meters per second squared j hat. We get 9 meters per second over 7.5 meters all squared times 3 meters in the I hat minus 2 times 9 meters per second over 7.5 meters times 6.6 meters per second in the I hat. And that results in a final result of 20.16 I hat plus 2 j hat meters per second squared. So now we see that despite our velocity still remaining in the j direction, despite the car going forward with no turning, the acceleration we view from the drone is not only in the j direction, it actually has a large I component.